So, in order to understand catalysts, we have to understand collision theory of reactions. So the GIF here shows that you have A and B, two different particles, moving together in a container with a certain speed/kinetic energy. You can use the terms interchangeably when we talk about collision theory. Because the mass of the particles is going to remain the same, therefore the only thing that affects the kinetic energy is the change in velocity. That corresponds to the temperature, if you remember. So, principles to remember: particles at a high temperature have more energy, therefore moving at faster speeds. Particles colliding at faster speeds are more likely to overcome any electron repulsions and react, because you have to remember that all of these particles are surrounded with clouds of electrons, and if these clouds of electrons are brought into close proximity with one another, they are most likely going to repel, they're going to move away from each other, which is the opposite of what we want. We want them to form a chemical bond. You can think of it as if you have two repelling magnets, the north and the north side of two magnets coming together. As you bring them closer together, they repel. But if you apply enough of your own energy, you can force them to hold together. So high temperatures is like forcing things that normally repel to come together and form an interaction. Now, the other thing to note about collisions of reactions is that it is very important for particles to collide with the correct orientation. So if you have a look, the thing that we're trying to make is NO2 in the bottom right here. You can see the circle has just gone around it. As such, we need the nitrogen monoxide and the O3 ozone on the left to collide with the right orientation. If they don't collide in the right way, then they're just not going to work. You can think of two puzzle pieces. So when you're making a puzzle, you know, the kind you make with like grandma, grandpa, old people on a table. Well, if you have those two puzzle pieces colliding in the wrong way, even if they are the right fit for one another, like they have the right groups that can join, like one sticky out bit and one hole, if they don't collide in the exact right way, they just won't stick together. So to reiterate, reactions need collisions to happen with enough energy to overcome electron repulsions, and they need to happen with the correct orientation. So, how does that correct to our catalyst and our Boltzmann distribution graph, which is what we're first looking at here? So, a Boltzmann distribution graph just shows how the speed, the kinetic energy of particles changes as temperature changes. So as you increase the temperature, the number of particles with higher kinetic energy increases. So if you see for 100 Kelvin, the fastest molecular speed any of those particles has is well below 1,000 meters a second. But if you go on to 1,000 Kelvin, you can see some particles with molecular speeds of well over 2,000 meters a second. So at higher temperatures, particles are moving faster with higher energy, and they are therefore more likely to react. See, the average kinetic energy is shown by the peak in the graph. So for 100 Kelvin it's there, 300 Kelvin it's there, 600 Kelvin it's there, 1,000 Kelvin it's there, etc. So, what we're going to try and envision is inside our reaction container we have two particles trying to react, A and B. Now remember that A and B are surrounded by electron clouds, which I've shown with a golden cloud-like shape, and they have to collide in the exact right orientation, which I've shown with the triangle and the Pac-Man, which means that if A and B collide backwards, they are not going to react. And remember that inside our container, our particles whizzing around are free to spin or to do whatever they want. So the likelihood of a correct collision at this point is not particularly